And when we talk about the orientation of elimination, that is what we have seen, like where the double bond will be formed. So, Hoffman had actually identified one particular system in which when a quaternary ammonium hydroxide undergoes decomposition, the preferential formation of the principal olefin is the smallest number of alkyl substituents. So, in the previous case whatever we have seen, we got the more substituted alkene as the major product, but what Hoffman identified was the less substituted alkene is the one that is formed in large quantity. So, in other words, the smallest number of alkyl substituent is the major product that is formed, and this is the observation by Hoffman in 1851. And in 1875, another scientist, Zaitsev, had identified that the more substituted or the more branched product is formed in large quantities. So, when we use secondary or tertiary alkyl halides, the preferential production of the product of that ethylene which carries the largest number of alkyl substituent is formed. So, this is what scientist Zaitsev had actually identified. So, that means we have two contradicting results. In one case, the terminal alkene is formed as the major product. In another case, the internal alkene with more substituents are formed as the major product. So, our major question here is why the same general reaction governed by two contradictory rules, that means Hoffman product and Zaitsev product. What is the driving force for this? Let us look into that. So, if we compare the two reactions, the Hoffman product is formed by a bulky leaving group, that means NR3 is the leaving group in his particular case. Whereas, in the case of Zaitsev product, we have a relatively small leaving group, that means halide ion is a much smaller group compared to N trialkyl group. So, that is the reason the Hoffman product formation is favored by bulky leaving group, and again Hoffman reaction is carried out, the initial reaction was carried out in the presence of silver oxide, which is also a very bulky base, and also other bases like tertiary butoxide are used, which again is a much bulkier base. So, whenever we use a bulky base, that leads to Hoffman product. That means, let us put us here, this is the terminal olefin. So, the terminal olefin is formed in the Hoffman mechanism or Hoffman type reaction. That is because we use a bulky leaving group, we use a bulky base. And in the case of Zaitsev product, we use a linear base or a smaller base. So, sodium ethoxide is a linear base. This leads to the more branched olefin formation. And when we look at the Hoffman product, these are mainly used in the structural analysis of natural product, because Hoffman degradation is one of the important method by which many alkaloids are studied. So, there he used this procedure to identify the structure of various natural products, whereas the Zaitsev mechanism is mainly used to study the E2 elimination type of reactions. And the Hoffman products are formed when we have a poor leaving group, whereas Zaitsev products are formed in the good leaving group, and Hoffman products are mostly controlled by kinetics, whereas Zaitsev products are controlled by thermodynamics. We will look at what is the kinetic and the thermodynamic product in the later part. Let us look at what are the factors that influence the E2 elimination. When we look at the structure of the alkyl halide, we already know the substituted alkyl halide plays an important role, because we also know the element effect earlier. So, that means if we change the alkyl halide, that means iodide or bromide or chloride or fluoride, depending on that the reaction rate also changes. Similarly, when we have a alpha branching, that means if it is a tertiary alkyl halide or a secondary alkyl halide or a primary alkyl halide, that also makes a major difference in the reactivity. And if there is a alpha branching, that also affects the rate of the reaction compared to beta hydrogen. So, these are all the structures that are present in the alkyl halide which affect the reaction. And in the case of bases, basically stronger bases favor the faster reaction, because the base is involved in the rate determining step. So, the stronger the base, the faster the reaction. and the stability of the leaving group is also very important. That is what we have actually seen. The element effect is one which actually favors, that is the leaving group ability to leave. Also when it increases, the rate of the reaction also increases. And when we talk about the type of solvent, basically polar aprotic solvents are preferred for E2 elimination, because why we have to use a aprotic solvent? This reaction does not have any ionic species involved in it. Basically for the carbocation mechanism or the carbanion mechanism, where we talk about E1 or E1 Cb, there we have ionic mechanism, but in the case of E2 mechanism we only have a transition state. So aprotic solvents actually favor this particular type of reactions. Now the minion asked the question like, sir, you said more substituted halides reacts faster, but why? The reason, let me explain. In the E2 reaction, basically there is a change in the hybridization at the reaction center. So this is one particular reaction center, that is another reaction center. So these two are basically having sp3 hybridization in the starting material. When the reaction proceeds, they are converted into sp2 hybridization. So that means in sp3 case we have 109 degree, 5 minutes is the bond angle, whereas in the case of sp2 we have 120 degree. So that means there is a normal relaxation which is happening in this particular case. So that means the crowding in the substrate is actually reduced when the reaction actually proceeds. So more highly substituted systems undergo elimination more readily, because the steric region actually pushes. If there are more congestion in the reaction starting material, that means elimination actually produces a much relaxed product. In other words, the 109 degree 5 minute carbon is now getting converted to a 120 degree carbon. So that means there is a huge around 10 degree space is available. That means more bulkier substituents actually undergo much faster reaction, because there is a better relaxation after the reaction is over. This is how we have actually shown here. So this is a primary substrate, and here it is a secondary substrate. In the secondary substrate we have a methyl group and a hydrogen atom. So the relaxation which is obtained in this particular transformation is very high compared to a primary substrate. So that is the reason more highly substituted systems undergo elimination more rapidly. And when we talk about the reactivity, the stable alkenes are formed faster, and the product basically primary, secondary to tertiary, the more branching means faster product formation. We can also say faster reaction rates. So here if you look at the reactive rate of the primary, this is ethyl bromide, and this is also another primary. We have a secondary, we have a tertiary, alkyl halides are there. So here the change of beta hydrogen also is present. So which says that in this particular case we have a less substituted product that is formed. The relative rate is taken to be unity. So the rate is smaller. Here we have a mono substitute, that means branched one. We have a double bond with one methyl group that is present. So that means the branching increases the stability. So that is the reason this relative rate is much higher in the case of propyl bromide compared to ethyl bromide. And when there is another additional thing like more number of beta hydrogens are present in the case of secondary alkyl halide, the reaction is still higher. But when we go to a tertiary alkyl halide, the reaction is very high, because we have a too much crowding in the starting material, which is comparatively relieved in the product. So that is the reason this undergoes reaction much faster. And when we talk about the beta hydrogen and the branching, actually the branching outweighs the number of beta hydrogen. So that is what is another important thing which is involved in the product formation and the rate of the reaction. When we say primary substrates which are less branched, they react slower compared to tertiary, which reacts much faster. And when we talk about the product stability, the primary gives a less stable product compared to tertiary, which gives a more stable product. So this is formed in a much faster way. And let us recap all the things what we have seen so far. When we talk about the E2 elimination mechanism, this is a bimolecular mechanism. That means the starting material and the products are actually involved in the rate determining step. and this is a single step mechanism or a concerted mechanism, and the stereochemistry is basically the anti-periplenarity leads to elimination that we have seen. Since there is no carbocation formed here, so there is no rearrangement in this particular case. So the rate, as we mentioned, depends on the substrate and the base concentration only. And when we talk about the relative reactivity, methyl reacts faster compared to primary, followed by secondary, followed by tertiary. And the relative stability of the alkenes, we already know the tetrasubstituted alkenes are more stable compared to unsubstituted alkenes. And as we mentioned, aprotic solvents are preferred for the elimination reaction.